Hi again, everybody. This is a somewhat brief summary of the activity we did in class today. We looked at these groups UN, which you remember were the multiplicative groups of Z mod NZ. So all the elements in Z mod NZ which are invertible under multiplication, not addition. We know everything's invertible under addition, but under multiplication there's not so many. And one of the tricks that people notice today, as you're looking at Z mod NZ and you're asking, oh, which of these elements are invertible, which aren't under multiplication, it turns out if you take the representative and it's relatively prime to your n, then it's automatically going to be invertible. And if it's not relatively prime, it's not going to be invertible. So as an example, when we look at n equals 5, well, you're looking at the 5 representatives, 0, 1, 2, 3, and 4. And, well, 0 is just never going to be invertible. And the other numbers, 1, 2, 3, and 4, are relatively prime to 5, because, well, 5 is a prime. In fact, whenever you have a prime here, you're going to get all the non-zero representatives, no problem. For 8, well, you have 0 through 7 originally. As usual, we toss out 0. But then you also have to toss out all the even numbers. They're not relatively prime to 8. But all the odd numbers are. And for 15, well, we can't be so easy to just toss out all the evens, because, well, let's see. 15, let's see, it has 2 prime factors, 3 and 5, so we have to get rid of all the stuff that has a 3 or a 5 dividing it. So 1 and 2 are okay, we get rid of 3, we get rid of a 5, 6, because that's got a 3, we get rid of a 9, that's got a 3, 10, that's got a 5, 12, that's got a 3, let's see, yep, that's all of them. Okay, so we're left with 8 elements here. So, what we wanted to do in these 3 cases was determine what the isomorphism type of the underlying group was. So what we noticed is if we could compute the orders of the elements, that would give us a really good indication as to what the group was going to look like. And I told you in the beginning, they're all going to look like cyclic groups or direct product of cyclic groups. And the reason why, ultimately, is that if you have any finite abelian group, it's going to be either a cyclic group or a direct product of cyclic groups. That's a result called the fundamental theorem of finite abelian groups. We're going to prove that next week. All right, so let's take a look at these orders so we can get a good idea. So, well, it's pretty easy. The identity element under multiplication always going to have order 1. We can do that for all these right off the bat. All right, how about for 2? Well, what we can do is go over here and do a little scratch work. We'll just start taking powers of 2 until we get back 1. And remember, of course, we're working modulo a number. In this case, we'll be working mod 5. So if we do 2, we square it, we get 4. We multiply it by 2 again, we get 8. But mod 5, that's going to be 3. Multiply it by 2 again, we're going to get 6. But mod 5, 6 is going to be 1. All right. So this tells us it takes 4 powers, right? 4 opportunities before we're going to get back to 1. So the order of 2 is 4. Now we could continue going with this, but there's really no need to. What we see already is we have a group of order 4, and we have an element inside of it of order 4. Automatically, the group must be cyclic, right? What does cyclic mean? It means everything is going to be a power of one element. But as soon as you have an element whose order is a power that is the entire group order, automatically, well, look at all the different outputs you get. 2, 4, 3, 1. We're getting all of the different elements. So we, with great confidence, can write down this is going to be a cyclic group of order 4. Now I write isomorphic 2. Right? These are not the same group, right? C4 might be just generated by some X or something. These are different. How would we build an isomorphism? Right? Well, of course, we want to build a homomorphism. What we would want to do is take a generator. In this case, we could say take 2. And we would send it to a generator for C4. And we proved, or we at least stated last week, that if you have generators and relations for your group, you can build a homomorphism by just defining it on the generators and showing that the relations are satisfied. And in this case, the relations we have to worry about are first, well, whatever we send it to, when you raise it to the 4th power, you should get the identity. So if we send 2 to a generator for C4, that'll be true. And the only other relation in this group is that you have commutativity. And of course, C4 is a commutative group also. So there's not going to be any worry about that relation holding. All right, so we'll be able to build a nice homomorphism. We would want to be able to check that we would get everything in the image, and that's easy. If we send this to X, of course we'll be able to get every power of X as well. So it'll be an onto map, and since everything's finite, it'll be a bijection, and hence an isomorphism. All right, so let's go down to the U8 case. Again, we only end up with 4 elements. So we might think, hey, easy enough, it's going to be cyclic group of order 4 again. All right, let's check. Let's start with 3. If we take powers, the next power is going to be 9, but modulo 8, that's a 1. So it's already back to a 1 after one time. That's a 2. Okay, so that's definitely not a generator for the whole group. All right, let's try 5. So if I start with 5 and I square it, I get 25. Modulo 8 is 1. 5 has order 2. All right, now, I could continue on, but actually I can stop there. If you watch the video that I just posted on cyclic groups, you know that for any cyclic group of order n, if you have a divisor d, there's a unique subgroup of order d in that cyclic group. Okay, well, we have a group of order 4. Let's say it was a cyclic group of order 4. Well, 2 divides 4, so there should be a unique subgroup of order 2. That means there can only be one element of order 2 in the whole group. And I just found 2 elements of order 2. That means this is not a cyclic group of order 4. Well, what's the alternative? Well, the only other group of order 4 we've seen so far is the light switch group, C2 cross C2. And sure enough, that's what this is going to be. And how would we end up proving it? Well, again, we would take 2 generators. Actually, 3 and 5 will generate this. Well, how do we show that? Well, we already get 1. It's the square of either of these. How do we get 7? Well, 3 times 5 is 15, which modulo 8 is 7. So the product of these will give you 7. So these will generate the whole group. And we would have to send them to 2 generators that we pick from C2 cross C2. And it'll work in the same way that we worked up here. All right, one more example. Let's look at n equals 15. So in this case, there's 1, 2, 3, 4, 5, 6, 7, 8 elements in the group. So we might think, oh, C8, that could do it. Or, well, let's see, it could be a cyclic group of order 4, direct product with a cyclic group of order 2. Or there's another possibility, it could be a cyclic group of order 2, cross a cyclic group of order 2, cross a cyclic group of order 2. So there's 3 possibilities. How are we going to figure out which one it is? Let's check the order of the elements. So let's start with 2 here. Well, if I take powers 2, I get 2, 4, 8. Now the next one is 16, which modulo 15 is 1. Okay, so I have an element of order 4. All right, let's check 4. I get 4, oh wait, 16, that's already going to be a 1. So that has an element of order 2. Okay, so I have an element of order 4, an element of order 2. That doesn't really solve it for me, so let's check 7. 7, okay, then it becomes 49, which mod 15 is 4. Now I've already seen what happens once I get to a 4. If I square it, again, I'm going to get to a 1. So the order of 7 is going to also be 4, just like 2 was. Alright, so I have 2 elements of order 4, 1 element of order 2. Let's check 8. 8, okay, you square it, you get 64, which modulo 15 is also 4. So 8 is going to have order 4 as well. Now, we could keep going, but actually right now we can identify what the group is. If this was a cyclic group of order 8, then, by the lemma I proved in the other video, there's a unique subgroup of order 4. Now, how many elements of order 4 are there going to be in a cyclic group of order 4? Well, there's the generator, that has order 4. If you square it, that's only going to have order 2. If you cube it, that's going to have order 4 again. And if you raise it to the 4th power, you get the identity. So you have 1 element of order 1, the identity. You have an element of order 2 in the middle, but then you have 2 elements of order 4. So in total, we could have at most 2 elements of order 4 in a subgroup of order 4, and there would only be 1 subgroup of order 4 in a cyclic group of order 8. But we already have 3 different elements of order 4. So we can conclude this is not a cyclic group of order 8. Also, well, there are elements of order 4, so it couldn't be a cyclic group of order 2 cross a cyclic group of order 2 cross a cyclic group of order 2, because every element in C2 cross C2 cross C2 has order 2. Well, there's only one choice left. We have to have a cyclic group of order 4, because we know we have elements of order 4, cross a cyclic group of order 2. Again, how are we going to prove such an isomorphism? Well, we would want to take a generator that corresponds to the C4 piece. So we need an element of order 4. Say we take the 2. And we'll send it to the generator for C4. Then we need to find something which we can send to the generator for C2. So we better take an element of order 2. Now, we got to be careful here. If we choose this element, that's not going to be a good one because it's already a power of the first generator we chose. Right? 4 is just 2 squared, which would mean 4 would be sent to the generator of C4 squared. We don't want that. So we need a second element of order 2. Well, let's check 11. If you square 11, you get 121, which is 1 modulo 15. So this is a second element of order 2. And if you remember, when we looked at the powers of 2, none of them were 11. So this 11 really will be a nice independent generator. And between 2 and 11, you can show you get all the different elements in this group. They really will form a generating set for our group. So we'll send 2 to a generator of C4. We'll send 11 to a generator for C2. That'll give us a homomorphism. We check all the relations. There's not so many things to check. And again, we'll be able to check it's an isomorphism by showing that we get every element in the image. Again, not so difficult to check. Right? So these are 3 good examples of how we're going to analyze a group like a UN. Remember, we're using Lagrange's theorem implicitly every time we're talking about orders. We know it has to divide something. We're using this wonderful property that cyclic groups have unique subgroups of any order dividing it. So a lot of good ways of tying all the theory we've done so far into some of the applications.